Let's see if we can maybe get that more focus. Much better. So last time we were talking about antiderivatives. Antiderivatives. And really, all there is to say currently is that for things you know how to take the derivative of, you can get some result. You also know how to take the antiderivative of that result by just going the other direction. And we don't really have much methodology at this juncture, right? Or just like things we already know how to differentiate, we know how to take the antiderivative of the derivative. What I would really stress, the kind of important crux of knowledge here, is that understanding that these two things or operations undo each other. Differentiation, in fact, I should write this down. Differentiation, and anti-differentiation, so many letters, undo each other. Or said another way, if you do both of them in succession, you'll end up almost where you started. Usually where you started, or you might be off by a constant. Let me show you two examples. Let's say our function is 3x squared plus 5x plus cosine of x. I can start by first finding the antiderivative. This desk is too low. I should not be bending over like that. So the antiderivative, which again, if we don't have the notation for it, we're still kind of pretending like we don't. We'll just call it capital F of x for a second. Capital F of x is going to be the antiderivative of f of x. So for these powers of x, for 3x squared, we're going to get 3x to the 2 plus 1 divided by that new power. Plus, for the same thing here, 5x to the first, we're going to add 1 and get 5x to the second divided by 2. And then for cosine, we just have to know what the antiderivative of cosine is. It's sine. And then we also add on a plus c. I would personally prefer to simplify this. I would like to write it as just capital F of x equal to x cubed. Plus, you can go a couple different ways here. You can write 5 over 2 times x squared. You could write 2.5. You could write 5x squared over 2. Any of those is fine. And now it may seem a little bit ridiculous to then undo what we've just done, but that's the whole point. The whole point is that if you do the antiderivative of the function and then you take the derivative of that, you should end up exactly back where you started. So if we take the derivative of capital F using the power rule, we're going to get, okay, 3x squared plus 5 halves times the derivative of x squared is 2x plus the derivative of sine of x is cosine of x plus the derivative of a constant is 0. And that is exactly 3x squared plus 5x plus cosine x, which is where we started with the f of x. On the other hand, if we do the derivative and the antiderivative, but in the opposite order, I mean, we're going to do the derivative first and the antiderivative second, we don't end up exactly back where we started. What do I mean? I mean this. I'm sure we might as well use the same function. So if we're starting off now with our function being, also, I'm much more likely to get off the screen here because I'm not on that little white thing over there. So if I'm off, please say something. But hey, James, I can't see what you're writing. If we start off with our function being 3x squared plus 5x plus cosine of x, and we first take the derivative of that's going to be 3 times 2x plus 5 times 1 plus the derivative of cosine of x is negative sine of x. I would certainly write, if I'm writing plus here, I would have actually waited and be like, oh, the derivative is negative sine, so I just write minus sine. Since I already wrote the plus sign, I write plus negative sine of x, which feels terrible to write, which I would then have to force myself to simplify as 6x plus 5 minus sine of x. Now, if we go back and take the antiderivative So and I am going to use the integral symbol here for the antiderivative because it's going to be a little bit different. The antiderivative of my derivative is going to be the antiderivative of 6x plus 5 minus sine of x. And we're going to end up getting 6x squared divided by 2. I do want to point out that when you anti-differentiate a constant like 5, you do get 5 times x, or whatever that constant is, times x. One way to think about that is, what we're saying here is the function is always the value 5, so the antiderivative has to be the straight line whose slope is 5, is one way to think about that. And then finally, the antiderivative of negative sign is positive cosine. But then we need to add on a plus c. So here, my antiderivative of the derivative of f of x is slightly different than what we started with. It's 3x squared plus 5x plus cosine of x plus c. Whereas the original function didn't have a plus c, or could have had a different constant added to it. It's not a big deal, but I did just want to point out that slight difference, that when you first anti-differentiate, then differentiate, you end up exactly back where you started. Whereas if you do the things in the opposite order, if you first differentiate and then anti-differentiate, you'll still almost end up back where you started, but there's a plus c here that wasn't there before. That's the only difference. But really, the big picture, the big picture is that differentiation and anti-differentiation do what? They undo each other. Exactly. That is the whole point. That is all the reason why we're talking about this. Sorry. So, where to next? So we're certainly going to come back around to, like, anti-differentiation is not going away. We're just going to take a side trip to talk about like area and some physical applications, so then we can come back to talking about anti-differentiation in more detail with more different methods of how to do it. But yeah, let's go ahead and talk about area under the graph. So how do I want to do this? This is where my drawings are going to be, unfortunately, maybe not up to par, but we'll live. So area under the graph. I should pause for a second. Just want to remind you all, or for those of you that weren't here on Wednesday, because we didn't have class on Friday, please ask questions if you have them. I'm happy to slow down. I'm happy to say things. I'm happy to go in a different direction if there's something else that needs to be covered. But my intent today is to talk about area under a graph. Probably working towards the limit definition of the integral. We'll see if we get there today. So let's look at an example. We're going to estimate or approximate, whichever word you like to use, the area under the curve f of x equal to the square root of x between x equal to 0 and x equal to 16. And usually we're given some direction as to how to do this. We're going to using 4 approximating rectangles. There's even more to be said there, but we'll do that in a second. And so this first one, for this first approximation, we're going to use right endpoints as sample numbers. Let's draw a picture. Not that you need to draw a picture when you do this necessarily, but it's helpful to kind of see what's happening and understand what we're going to get. So it's the usual square root function. I should grab some different colored pens. Looks like this. Grab some other colored pens there. Somewhere. Put that up right now. Yeah. Don't fall. So we've been told to use 4 approximating rectangles. Our intervals from 0 to 16. And what we're going to do is to approximate this area here, we're going to divide this area up into 4 subsections or subintervals, usually, but not always, of equal width. So the way we do that, the way we find what we typically call our delta x, that's going to be your 16 minus 0, the whole width of your entire interval, divided by your n, the number of rectangles or subintervals that we want to use, which in this case ends up being 4. I'll point out that more generally, we say that delta x is equal to b minus a divided by n, where in this example, 16 is our b value, 0 is our a value, and our n is 4 because we're using 4 approximating rectangles. So we're going to divide from 0 to 16 up into 4 equal subsections, which each have a width of 4. So we're going to go from 0 plus 4 to 4, 4 plus 4 to 8, 8 plus 4 to 12, and 12 plus 4 to 16. And I'm just going to draw the picture right now. Let's do it this way. So here's my first subinterval from 0 to 4. And in that interval from 0 to 4, we've been told that we want to use the right endpoint to estimate the area of that subinterval, or of, I should say, the area under the curve in that interval. So from 0 to 4, the right endpoint is 4. We're going to plug in 4, and that's going to give us the height of our rectangle. So this rectangle, which is a gross overestimate, that rectangle is what we're going to use for our first subinterval. So if we start writing our approximation, here's some pretty typical notation. I'm going to call this R4, R for using right endpoints, 4 for the number of subintervals. That's going to be equal to, well, my first rectangle has a base of 4, has a height of whatever I get when I plug 4 into this function. Oh, what's this function again? This function is f of x equal to the square root of x. So when I plug in 4 here, I'm going to get the square root of 4, which, yes, is 2. Plus, we're going to do it again, right? For this next subinterval, we're again going to use the right endpoint, which is 8. That's going to be the number we plug into the function to get the height of the rectangle. This rectangle has a base of 4. A height of 8 plugged into this function is going to be the square root of 8, which is not a nice number, right? It's just whatever it is. It's about 2.8. And so on. For the next subinterval, again, using the right endpoint, we're going to get an overestimate. It's going to be a base of 4, a height of, if we plug in 12, the square root of 12. And finally, when I plug in 16, I should draw the picture first, sorry. For this last rectangle, the base is again 4. The height is the square root of 16. That's going to be 4 times the square root of 16. And let's see if I did myself a favor here. I did, cool. So simplifying this, you get approximately, I'm just going to write that. It's going to be about 49.17. Definitely an overestimate of the total area. Question. Are right endpoints always going to give us overestimates? Well, I would say the answer is no. More generally, I'd say the answer is yes if your function is increasing. So if your function is always getting bigger from left to right, then the rightmost point is always going to give you an overestimate. But if your function was getting smaller, the right endpoint wouldn't give you the overestimate. We'll look at another example in a minute where it's a decreasing function and the right endpoints actually give you the underestimate instead of the overestimate. Let's do this sort of same thing, except let's go ahead and find out what our estimate's going to be when we use left endpoints. So using left endpoints, I don't want to draw it again because my drawings don't get better. But you can if we look here, you can kind of actually see that if I use the left endpoint, well, the first rectangle, the left endpoint feels kind of silly. Because for the first rectangle, the left endpoint has a height of 0. So my first rectangle is not really a rectangle. It's just a rectangle that failed to being a rectangle. It's got a base of 4 and a height of 0. So my L4 is going to be 4 times the square root of 0 plus, now the next one, the left endpoint between 4 and 8, we're going to use 4. We're going to plug in 4, and that's going to give us the height there. So there's my underestimate using the left endpoint for the second interval. That's going to be a base of 4 times the height, which now we're plugging in 4 instead of 8 to the function. Next rectangle, same deal. Between 8 and 12, I'm using the left endpoint, which is 8, plugging that in, getting a height of the square root of 8, and there's the area I'm calculating. It's going to be my base of 4 times my height, which is the square root of 8. And finally, for the last rectangle, I'm using the left endpoint, which now is going to give me still a base of 4, but my height's going to be, if I plug in 12, the square root of 12. This is going to be approximately equal to 33.17. Definitely an underestimate. So a few questions to ask ourselves here is, or I should say the most important question is, how could we make our estimate better? Any thoughts? Totally. And that's what we typically are going to do when we work things. I will say another good answer, but that's not what we're really looking for, is you could average them. That's also a way of getting a better estimate. It's still not like going to get you exactly there. But yes, we could use more rectangles. So drawing the pictures gets to be kind of messy. So let's just think about for a second. If instead of using 4 rectangles, what if we used n equals 8 rectangles with right endpoints? So I don't really, I mean, yes, we can draw a picture, but really the important part is kind of knowing what values you're plugging into your function. So I'll remind us our function is the square root of x, and we're on the interval from 0 to 16. I'm just going to draw the interval part because that's really what's helpful to me. Here's 0, here's 16. My delta x in this case is my b minus a divided by n, which is 16 minus 0 divided by 8, which is 2. So all of my subintervals are 2 away from the next one. So it's going to be 0 to 2, 2 to 4, 4 to 6, 6 to 8, 8 to 10, 10 to 12, 12 to 14, 14 to 16. It's easy when they're integers. It's less nice when things start to become fractional, but still totally doable. So if we're using right endpoints with our 8 subintervals, we're just going to do the following. Our estimate of the area using 8 right endpoints is going to be my base times my height, plus my base times my height, plus my base times my height, plus my base times, how many times? 8 times. So it's going to be my base, which is 2 in this case, right? My base is 2 times f of 2, plus my base, which is still 2 times f of 4. It's going to be 2 every time because we're typically using intervals with an equal width. I don't want to write all this out. So I'm going to cheat kind of and write just 2 times f of 2 plus 2 times f of 4. Maybe write the last 2 in there. 2 times f of 14 plus 2 times f of 16. If I was trying to write this a little bit more simply, I'd write it as 2 times square root of 2 plus square root of 4 plus square root of 6 plus all the way to the square root of 16. No one really wants you to bust out the calculator and approximate that. If that's done, you can hand it to me. Did everybody get a chance to write their name on this? Cool. If you didn't, you can always grab it at the end of class. And I'm trying to remember if I actually wrote this down before or not. Ooh, lots of papers here. So here, if we simplify this via calculator, we get approximately 46.12. Still an overestimate because we used right endpoints for this increasing function, but a less bad overestimate, right? Our previous overestimate was, I forget, it was 49.17. So we got closer to the number we don't actually know. In a similar way, oh, actually, yeah, I might as well. So what I really kind of want to point out here is that we could make this even easier to write by using what's called sigma notation. So when you're trying to add up a bunch of things and you don't want to write all the things you're trying to express that you're adding up, there is a compact way of writing that. It's kind of like using a function. So another way to write this is to say, well, I'm making a sum, capital sigma, and we usually start at 1, although you can start really anywhere you want. For people who have seen this in class already, are they using I's or K's for subscripts? Okay. I usually use I as well. So we're going to go from I equals 1 to, well, how many terms do we want to add up? I know I didn't write them all out, but we know it's how many? It's 8. So we're going to go from I equals 1 to 8, right? 1, 2, 3, 4, 5, 6, 7, 8 counts 8 things. If you end up starting at 0 and you want to count 8 things, well, then you need 0, 1, 2, 3, 4, 5, 6, 7. So you could go from I equals 1 to 8. You could alternatively go from I equals 0 to 7 and still count up 8 things. Counting's kind of weird because, right, if you subtract the numbers, 8 minus 1 gives you 7, but you've really counted 8 things. It's kind of funky. Here, we know we need this 2 multiplied by each thing, and then we need the square root of something. But something that's going to change. I just got a message, so that's weird. Anyway, not your guys' problem. So when I plug in 1, I want to get 2 in the square. When I plug in 2, I want to get 4. When I plug in 3, I want to get 6. It seems like I need 2 times whichever interval number I'm on. And that's going to work. If I plug in 1, I get 2 times the square root of 2 times 1. Plus, because that's what this sigma notation means, is you plug in your subscript, or your index is actually the right word here. And then after you plugged it in, you add, and then you do it again for the next integer, which is 2. And you get 2 times the square root of 2 times 2. Plus, then we plug in 3 and get 2 times the square root of 2 times 3. And so on, and so on, and so on. Until the very last one, which is 2 times the square root of 2 times 8. Which is exactly the same as up here, just written slightly differently. Question? Totally, yes, that's actually an excellent point, is that when you have constant multiples of things, you can totally bring those multiples out in front. Yeah. So we could also have written this as 2 times the sum from I equals 1 to infinity, not to infinity, upright infinity, 8 of the square root of 2i. That would give you the same thing, because then the 2 just hangs out. And plugging in 1, you get the square root of 2 times 1. Plugging in 2, you get the square root of 2 times 2. Plugging in 3, you get the square root of 2 times 3, all the way to the last one, which is the square root of 2 times 8. Same thing as this, right? We've just factored out the 2. So factoring out the 2 from this means you're putting the 2 in front of the sigma notation here. We'll definitely come back and talk more about this, but it felt like an opportune moment to kind of say something about it. Excuse me. And then, yeah, we'll squeeze it in here. In a similar way, we could say that the estimate using 8 left endpoints is almost the same, right? Instead of starting at 2, though, right, for the first interval from 0 to 2, instead of plugging in the 2, we're going to plug in the 0. And then for the next interval, instead of plugging in the 4, we're going to plug in the 2. So it's going to be starting here in the same sort of way, 2 times f of 0 plus 2 times f of 2 plus all the way to 2 times f of not 16, right? We don't go all the very last one from between 14 and 16. The left endpoint is 14 that we're plugging in. And then, did I write it down? I did. That's going to be approximately 38.12. And I'll point out here, you could totally write this as 2 times the sum. Now, here's where you could go a couple different ways. You could either say the sum from I equals 1 to 8, and then say it's the square root of, we want all of them to be 2 less. So literally take the same thing and subtract 2. That'll totally work, right? We plug in 1, you get 2 minus 2, which is 0. If you plug in 2, you get 4 minus 2, which is 2. If you plug in 3, you get 6 minus 2, which is 4. And so on up to the very last one. When you plug in 8, you get 16 minus 2, which will give you the square root of 14. Or you can write it as 2 times the sum from I equals 0 to 7 of the square root of 2i. That would also work just fine. Essentially, you're saying instead of starting at the first spot, I started at the one to the left at the 0 spot. Either way is totally acceptable. In fact, unfortunately, there's kind of a lot of different ways you can write the same sigma notation. Let's see. Did I have more to say about this one? Yeah, I do have more to say about this one. This example feels like it goes on forever. Yeah. So before we say more about this one, I do want to show you one other example though. Let's say, in fact, I would like you all to try one on your own for a moment. So let's say the function is g of x equal to 1 over x. We're on the interval from 1 to 7, and we want to use n equal to 3 subintervals with right endpoints to estimate the area. I'm going to draw a picture, but you all should start trying to actually not calculate it, but just express what that's going to be. So some base times some height plus some base times some height plus some base times some height. All right, let's take a look. So I'm using 3 subintervals. My interval is 6 wide. So I should have given myself more room. My b minus a over n is 7 minus 1 over 3, which is 6 over 3, which is 2. So each of my rectangles has a base of 2. So I'm thinking of like this being a delta x, and this being a delta x, and this being a delta x. From 1 to 3, from 3 to 5, from 5 to 7. So using right endpoints, well, if I'm on the interval from 1 to 3, my right endpoint is definitely 3. And when I plug in 3, my height looks like that. So there's my rectangle. It's going to be my base, which is 2, times my height, which is f of 3. And for the next rectangle, my drawing's going to be a little dicey here. And I plug in 5, my base is 2, and my height is f of 5. And thirdly, when I plug in 7, my base is still 2, my height is f of 7. So here we're getting 2 times 1/5. I should just factor out the 2. 2 times 1/5, sorry, 1/3 should be the first thing I'm writing. Got ahead of myself there. Plus 1/5 plus 1/7, which is kind of terrible, right? But we could add these fractions together if we really wanted to and get, ugh, yeesh. Okay, common denominator is not nice. It's 105. Multiply this by 35 over 35. Multiply this by 21 over 21. Multiply this by 15 over 15. And get something gnarly like 35 plus 15 is 50 plus 21 is 71. 142 over 105. It doesn't feel like it tells us a whole lot, right? I mean, I can see that, okay, that's about like 1.4-ish because we're dividing almost 140 by almost 100. But what it does certainly display is we have an over or an underestimate. It's definitely under, right? Look at our rectangles. They're definitely below the area that we're trying to, in fact, I could have drawn this a little bit better, right? We're trying to estimate this total area under the curve from 1 to 7, which is definitely more area in blue than in red, if you can see my so-so picture there. So I just want to reemphasize, right endpoints don't necessarily mean you get an overestimate. They don't necessarily mean you get an underestimate either. They do if your function is strictly increasing or decreasing. But if your function is like the sine function that does stuff like this, you're not guaranteed of an over or an underestimate. You just have an estimate. All right, where else to go here? Sure. Oh, yeah, we could say that as well. So I got lots of papers here. So one more thing to say, not one more thing to say. I don't think you need to draw this picture. Oh yeah, question. Definitely. So if I was writing a sigma notation, and I should kind of go more general here. If we're trying to get an estimate in general, if you're trying to find, say, like R3 using sigma notation, there's a very generic formula for this. It's the sum from I equals 1 to 3, or 1 to whatever number we're going to, or that's the number of subintervals, of your base times your height. Really, you should be thinking of it that way, right? We're just adding up areas of rectangles. Base times height, base times height, base times height. The base, which I'm not, well, the base, which I'm going to write second, the height, which I would usually write second, is going to be the function evaluated at your right endpoint or your left endpoint, whatever endpoint we're using. We typically write this as x sub I. X sub I? Yeah, that's what I usually write it as. People have different notations they use. I like x sub I. Your base is your delta x, very generically. So my x sub I here is, well, yeah, we can talk more about this. So usually when we talk about our endpoints here, your left endpoint, which is A, your A is your x sub 0. It's kind of like your initial starting place. And then each next right endpoint is going to be the next subinterval. So like here, our x sub 1 is 3. Our x sub 2 is 5. And our x sub 3 is 7, which is also our ending value. Right? Our intervals from 1 to 7, our A is 1, our B is 7, our A is also our x sub 0, our B is also our x sub n, whatever our n is, in this case, 3. So our A is x sub 0, which is 1. And then our x sub 1 is going to be 1 plus 1 delta x. I know you already know these numbers. I'm writing them down this way on purpose, though. Our x sub 2 is going to be 1 plus 2 plus another 2. Right? I'm adding 2 subintervals to get to the right endpoint that's 2 subintervals away. And in a similar way, x sub 3 is going to be 1 plus 2 plus 2 plus 2, which is 7. But generically, the way we think about writing our x sub I for the right endpoint is that x sub I is equal to our A plus I times delta x. A where we start, 1 in this case, and then we just are adding I, the number of subintervals we want to get to the ith right endpoint. So in this case, it would be 1 plus I times 2, or probably 1 plus 2I. And that works. If I is 0, you get 1 plus 0, which is 1, which is the 0th right endpoint, which is really the left endpoint. If I is 1, you get 1 plus 2, which is 3, our first right endpoint. If I is 2, you get 1 plus 4, which is 5. If I is 3, you get 1 plus 6, which is 7. So writing it out this way, we get the sum from I equals 1 to 3 of f of 1 plus 2I times our delta x, which is just 2. And then finally, replacing f of whatever with what the function actually, oh, I used f, I should have said g. Sorry, it's a very easy mistake to make. I called it g to start off with, and then because we use f all the time, I started calling it f accidentally. I should have called, well, I'm going to write g here. It's terrible. I feel mildly bad about it. And then fixing that, or not fixing it, but moving on, we have the sum from I equals 1 to 3. Our g function, our g of x is 1 over x. So g of 1 plus 2i is 1 over 1 plus 2i multiplied by 2. Yes, you can pull that 2 out in front of the sigma notation, but you do not have to. And that should give us the same thing that we got right here. If I plug in 1, I get 1 over 3 times 2. If I plug in 2, I get 1 over 5 times 2. If I plug in 3, I get 1 over 7 times 2, which is exactly what we have right here. 2 times 1 over 3 plus 2 times 1 over 5 plus 2 times 1 over 7. Yeah. Yes. Maybe. Actually, I'll slide this down. Sorry, there's a little like thing in the way here that makes it hard to slide it up. But yes. So why might we care about finding the area under a curve? Right? Like, what does it tell us? Well, it depends on what the curve was telling you in the beginning. One example of this is the following. Desk space here. Try to keep this on the page here. So suppose that the velocity of a car accelerating from rest is given by a function we've already talked about today. Is given by f of t equal to the square root of t meters per second, where we're letting time range between 0 seconds and 16 seconds. Use M4, this is the estimate using midpoints instead of right or left endpoints, to estimate the total distance traveled over this time period. Seconds. So let's take a look. And again, we're going to kind of come back to the picture that I said I didn't want to draw anymore. I'll still happily draw it. I don't mind drawing pictures. I just don't feel like I'm very good at it. But you know what? The way you get better is by practicing. So here's the function here where our f of t is equal to the square root of t. Since we're using t's instead of x's, we're going to call the horizontal axis the t-axis, and the vertical axis is our f of t. And we're going to divide this interval from 0 to 16 still up into 4 equal subintervals. From 0 to 4, from 4 to 8, from 8 to 12, from 12 to 16. But now, instead of using left endpoints or right endpoints, we're being asked to use midpoints. So for each interval, before we even think about plugging something in, we're going to find the midpoint. Pens of different colors. So between 0 and 4, the midpoint is 2. Between 4 and 8, the midpoint is 6. Between 8 and 12, the midpoint's 10. Between 12 and 16, the midpoint is 14. In other words, oh, one sec. In other words, you're finding the average of each of the 2 points. Okay.
If we're not using the number line version, what is the x sub I notation for finding?
Excellent question. So here, for the midpoints specifically, so it depends on what kind of points you're finding. So I would say very generically, let's just use a new piece of paper here so I don't try. I'm trying to stop myself from writing things off to the side because I'm trying to make my notes more scannable easily in like this program we're using. And when I write things off the side, they don't scan very well. So yes. So I would say for right endpoints, we talked about it already a little bit. The generic formula is that x sub I is equal to a plus I times delta x. Again, where your delta x is the usual b minus a over n. For left, it's almost the same. In fact, I would say it's literally your x sub I minus 1, right? You're just shifting one left and saying it's going to be a plus I minus 1 times delta x. And I might even write off to the side here where I is going from 1 all the way up to whatever your end value is. Same deal here. I is going from 1 to every. So it makes sense here that for your right endpoints, you're going to start at a plus 1 times delta x, whereas for your left endpoints, you're going to start at a plus 0 times delta x. We're going to start at 0 at a. And then for the midpoints, well, there's a reason I said they're the average. It's because they're the average. So if you take the average of x sub I and x sub I minus 1, you'll exactly get the midpoint for the ith subinterval. So I'm going to call it x sub I bar, because that's typical average notation, is the over bar notation. It's literally x sub I minus 1 plus x sub I divided by 2. Which you could then actually throw these into that formula and get an expression for that. So it's going to be a plus I times delta x plus a plus I minus 1 times delta x all over 2. Combining some terms, look at what we get. We get a plus a plus I times delta x plus another I times delta x minus 1 times delta x all over 2. So we get 2a over 2 plus 2I delta x over 2 minus a lonely delta x over 2. So that's going to be a plus I times delta x minus half of delta x. Which again, if you think about it, doesn't seem super surprising, right? You're essentially going to get the right endpoint and then going back half of the width of the subinterval to get your midpoint. I don't think that's the best way to do it, though. I actually think this is the best way to think about it, the first way I thought about it. So that's how we're going to get the midpoint. And again, I think it's easier to write out, like if you have nice numbers, it's super easy to find midpoints. If they're less nice, I still actually think writing it out this way is useful, because then you can kind of see what the midpoints look like. So here, check this out. Our approximating rectangles now look like they're not necessarily over or underestimates, right? There's the area that we're going to estimate for the first one. So our M4 is going to equal my first base, which is 4, times my height, which is f of 2. Then my next rectangle, the height's going to be given by plugging in 6. So it's going to be another 4 times f of 6. I'm going to be smart here. I'm going to pretend like I'm factoring out the 4 and add on an f of 6. And then for the next one, an f of 10. And then for the last one, an f of 14. So there's my estimate. Now, one thing I want to point out is my base is some change in time, right? From 0 to 4, we're saying 4 seconds have elapsed. So that's really a measure of 4 seconds, where these f of 2, f of 4, f of 6, f of 10, f of 14, those are all measures of velocity in meters per second. So whatever this adds up to, this part here is something measured in meters per second, some number of meters per second, which maybe I've written down here. Oh, I didn't quite write it down. That's all right though. It's 43.07 divided by 4, whatever that number is, approximately. But then when you multiply these things together, what units do we get? Well, when you multiply seconds by meters per second, the seconds are going to cancel and we get meters. And that's kind of the point here, is that when you find the area under the curve where the curve is representing some velocity, you end up finding the distance that vehicle or object traveled over that time. Or essentially, area under the curve of velocity is distance traveled. This ends up being equal to 43.07 meters. And again, that is an approximation of the actual distance traveled, right? Because we still haven't gotten to the exact value here. What I think about, and so here's what I kind of think about when I think about this. When you take derivative, like back in 17, we took derivatives, like if you had something representing something's position at a certain time, its derivative was the rate of change of position, aka velocity. And the derivative of velocity is how velocity changes as time goes on. So it's like meters per second per second. In other words, it's acceleration. So when you take a derivative, I kind of think about it as, I should say, when you take a derivative with respect to time, you're essentially dividing by a unit of time, right? Position goes to velocity, which is meters per second, or whatever units you have. Velocity's derivative goes to acceleration, which is meters per second squared. So you have another unit of time at the bottom. Anti-differentiation does the opposite kind of thing. Instead of dividing by another unit of time, you end up multiplying by a unit of time. So when you anti-differentiate velocity, you end up getting position. When you anti-differentiate position, you end up getting, well, that's kind of, okay, that's kind of, okay, the analogy kind of falls apart there a little bit, but the idea is still the same. Essentially, differentiation kind of divide by a dimension or you lose a dimension, and integration or anti-differentiation, you kind of get more dimensionality. You add a dimension. It's not like a super exact thing, but it is pretty true. And I should not try to say anything more because it is 1:59. All right, I'll see you all on Wednesday. Make sure you got your name on the sign-in sheet if you didn't already. I have office hours over in South Silo from 2 to 3.